Hello, welcome back to another episode of Quarantine Chemistry. Today we're going to finish up our notes for the week. We're going to talk about the kinetic molecular theory, always abbreviated KMT. So anytime you see KMT referred to in the book or as you're going through other YouTube tutorials, things like that, KMT is kinetic molecular theory. So what the heck is it? Well, it's an attempt to explain what gas particles are like based on how we see them behave in nature. There are 5 points of the KMT, and then that leads us to some unique properties of gases. So let's hit the 5 points of the KMT, and then we'll look at some simulations to figure out how they behave. So gases consist of very tiny particles in random ceaseless motion. Particle-to-particle collisions between gases and the container wall are elastic. That word elastic simply means that the overall energy of the sample is constant. So you'll see that the temperature of the sample will stay the same. Some individual gas atoms might speed up or slow down, but overall, the entire sample's kinetic energy, the energy of their movement, overall, you average it all out, it'll stay the same. Space between the particles is really big compared to the actual size of the gas particles. There's a lot of empty space. There are no attractive or repulsive forces between the particles in the gas phase, which means they don't stick together and they don't stick to the container. Kinetic energy, how fast they move, is directly related to Kelvin temperature. If you have a gas that behaves this way, follows all 5 of these points exactly, that's called an ideal gas. If we look at gases flowing, how do gases flow? Well, a gas flows because it has the ability to bounce off of things and move past things that gets in its way. They have really low density because of all the space that's in between those particles. So their mass per unit volume is really low. Remember, constant, random, ceaseless motion, tons of empty space in between, so they can be pushed closer together. Let's take a look at that real quick. So we take a sample of a gas. Notice all these particles, random motion. There's no set path. They start bouncing off of the wall. They start bouncing off of each other. They're not sticking together. If we put a different gas in there, it's able to move past the other gases. They move around each other. They're flowing, okay? Now, look at all the empty space here. That allows us to take this and smush it down. Now, that causes the pressure to go up, but it still allows the gases to be a gas. There's still empty space. There's still random ceaseless motion. They're still moving past each other. They're not sticking to each other. And if we notice how fast they move, watch what happens as we heat them up. Let's go way, way high. Look at how fast they're moving now. The temperature went way up. They're moving faster. So because of all the empty space in between them, they can be compressed. Liquids and solids can't be compressed. There's no empty space in between them. Expansion and diffusion. Because there's no attractive or repulsive forces, there's nothing holding the gas particles together. So they can spread out further and further and further. Basically, expansion is the opposite of compression. Instead of pushing them together, we can spread them out. So if we spread out, we make this container really big. Now we've just created more space. Why can we expand it like that? Because there's no attractive forces. If you have a syringe at home, even like something used for injecting flavoring into a chicken. You could ask your mom if she has a injector in the kitchen. Fill it up with water, put your thumb over the hole, and try to push the water closer together, or try to pull the plunger of the syringe out and see if it'll move. Will the liquid expand or compress? And you'll see that it won't. Now, last thing we need to talk about in this short little video here is the property which is called diffusion or effusion. Effusion is where these gas particles escape from a small opening in the container. And if you look here, you'll see that how fast the little ones are leaving is much higher than the heavy particles. And that's because they move faster. They're faster moving, so they're finding the small opening faster. This is what happens to a helium balloon when you get it and it's nice and tight, and then that mylar ends up getting weaker and weaker, and eventually your helium balloon kind of falls to the bottom. It's because somewhere in that balloon surface, there's a small hole, and these little particles that are lighter than air, they keep escaping out of that small hole. A gas escaping out of a small opening in the container is referred to as effusion. Now, let's look at one more thing, and this is diffusion with a D. Notice both of these samples have the same average energy, same temperature. Watch these numbers. Watch these numbers and watch how slowly the heavier neon moves into the helium side compared to the helium side moving into the neon side. Diffusion, how fast something diffuses, is inverse to the size of the particle. So the lighter particle should spread out faster. So let's open this up and let's watch that happen. So already 8 particles of neon have moved onto this side, but 15 particles of the helium have moved onto this side. That's twice as fast. The diffusion, spreading out, filling the container happened twice as fast. So in this quick little video, we talked about expansion and diffusion because there's no attractive forces. They can spread out. There's nothing holding the sample together. They will spread out to fill an entire container, but they will also escape through a small opening. That's called effusion. We talked about because they have low density, we can push the particles closer together because of all that empty space. They expand and diffuse. Hold on. They can flow because they don't stick to themselves or to the container wall. And then we talked about those 5 points of the kinetic theory. You don't have to memorize these, but you should be able to think about why gases behave the way they do. It is all because of those 5 points. That ends this episode of Quarantine Chemistry. If you have any questions, please shoot me a question in the comments below the video here, or shoot me an email, damascow@ptsdwebapps.org. Remember, do something today to make yourself better. Intellectually, physically, spiritually. Worst case scenario, do some pull-ups.